Hello students and welcome to this session. So this is part of a series of lectures where we will be revising the content of class 11th physics for you, and we will be starting with the topic of vector analysis and calculus. So this is going to be a series of lectures where we are looking at the key concepts of vector algebra and basic calculus that we require in physics. So, So keeping in mind that this is a set of revision lectures, okay? So we will be concentrating on the key concepts and some of the applications, but with um, while being mindful of the fact that you have studied these topics earlier, so we might not go a lot into the derivation of the various formulae, etc., but concentrate more on the applications because it's a review of concepts that we've learned already earlier. So let's begin straight away and let's talk about vectors. So just a quick reminder of the whole idea and concept behind vectors. So as you know, physical quantities can be divided into two categories, vectors and scalars. Okay. So all physical quantities that we deal with in physics are categorized into, at this stage, at this level of physics, they are categorized into either vectors or scalars. And by definition, you know, vectors are those quantities which are defined by both magnitude and direction. Okay, so these are defined by a magnitude and a direction. Common examples of vectors are things like forces or velocity or displacement or something like electric field, etc. Whereas scalars are simpler physical quantities because they are defined by just a magnitude. And common examples of scalars being, example, time, mass, volume, distance, pressure, density, electric current, and so on and so forth. Electric charge for that matter, electric current. So these are, roughly the categorization of physical quantities into vectors and scalars. Now, just as a part of your general information and knowledge, the categorization of physical quantities is a bit more complex at a higher level than this. There is a general category of quantities called tensors, and there are various different types of tensors. So actually, we say that vectors and scalars are actually categories of tensors themselves. And there are physical quantities or there are tensors which would be neither vectors nor scalars in the way they are described and the way they are defined mathematically. So this is just as per your general knowledge. This will not be covered. Tensors will not be covered as per your 10+2 syllabus. However, you should know that, you know, in certain situations, quantity like, let's say, moment of inertia of a rigid body in physics, or a quantity like a pressure field, it will have to be defined by a type of tensor where it would come in the category of neither a vector nor a scalar. So there are those type of tensors also. So in a higher sense or in a more general sense, we say that vectors and scalars are both categories of tensors, and they are like subsets of tensors, and tensors are more varying in their numbers and qualities. And there are certain physical quantities in certain situations which would neither come in the categories of vectors nor in the category of scalars. However, sticking to our 10+2 level, it is enough to say that, you know, physical quantities will have to be either or of these two. They will be categorized either as vectors or scalars. And these are the definition of vectors and scalars. So our focus over here is going to be more about the algebra of vectors, how we deal with representation of vectors and doing algebraic operations like addition, products, okay, subtraction, etc. of vectors. So let's get down to that. Okay. So the first and foremost aspect about vectors for us, once we've understood what are vector quantities, will be the representation of vectors. Okay, so let's quickly remind ourselves of the different ways of representing vectors. So as you probably are well aware of, the first method of representation of vectors is what we call the geometrical representation. So in the geometrical representation, a vector is just represented by an arrow. So a vector is represented by using an arrow, such that the arrow has two important properties. The arrow has a length. It has a specific length. So that length represents the magnitude of the vector, whereas the direction of the arrow, it represents the direction in which the vector acts. Represents the direction of the vector's action. So let's understand this. So if we draw a line with an arrow head, okay, then it becomes more specific than a line segment, because now it points in a particular direction. So this direction in which it points, that represents the direction, okay, and the length from the origin. Okay, so this point is called the origin of the vector, and this point here can be called the tip of the vector. So the length between the origin and the tip, this length would be proportionate to the magnitude, and the direction would be the direction of the vector. So let's do a quick exercise to understand this type of representation. Okay. So for example, if we have defined on our two-dimensional plane the system of geographical poles, as this axis represents our north and south, and this axis represents our east and west. Now we want to draw vector arrows to represent the following forces. Suppose we want to do a simple exercise like this, okay? So the first force we want to represent is force of, let us say, 20 newtons acting towards east, and let us call this force F1. Now, as you know that when we put an arrow symbol in top of a symbol, or of a alphabetical letter symbol, it represents a vector. Okay, so this symbol, as I'm sure all of you are aware, is the symbol for a vector quantity. And secondly, we want to represent a force of, let us say, 30 newtons acting northwards, F2. And next, let's say we want to represent a force of 50 newtons at 37 degrees north of west, F3. So we want to represent these particular vectors by drawing vector arrows. Okay, so we want to draw vector arrows to represent the following using this notation that this vertical axis for us on this two-dimensional plane represents the south to north and the horizontal axis represents the west to east. So let's get on with this. Okay, so what will happen is we'll have to draw individual arrows to represent F1, F2 and F3 such that those arrows contain this information. The length of the arrow should be proportional to the magnitude and the direction of the arrow should be along the direction in which the force is acting. So for example, F1 is acting towards the east. So how we will represent F1 now will become something like this, that with respect to our given system of reference, our force F1 will be a vector arrow that points towards east, and that should look like this. So its length will be such that it will be proportional to 20 newtons. And its direction is pointing towards east, as you can see. Now, in comparison to that, if you can see what we are doing for the force F2, it should now be northwards and its length should be 30 newtons. Okay. So its magnitude being 30 newtons. Now we'll have to draw a longer vector such that its length looks proportional to 30 when this one's length looks proportional to 20. So let's say our second vector is represented by this second arrow now. So you can see that because it's pointing northwards, it will have to be drawn perpendicular to this one. And now I'm drawing this roughly, remember, so I'm not going exactly according to scale, but the length of these two should be in the ratio 3:2, because this one's length, whatever the actual length, let's say L2 of this one, and whatever the actual length L1 of this one, what should happen here is that L2 is to L1 should be equal to 3:2, because their magnitudes are in the ratio 30:20 or 3:2 like that. Okay, and of course they are perpendicular to each other, as you can see. Now in the similar instance, now when I draw the third vector, now this is the one we have to be a little bit more technical about. Okay, because the direction is in terms of an angle. So the angle over here given to us for the third one is that it is 37 degrees north of west. Okay. So what does this mean? That from the west we have to point towards north. Okay, so this is the direction pointing towards west, this is the direction pointing towards north. So from west we have to turn by 37 degrees towards north like this. So this sort of direction, this is what we mean by it. So for that, this vector will now look like this. Its direction in comparison to these two will be something like this. And its length will be longer than these two, as you can see. So this is now 50 newtons. Length is L3. And make sure that we understand that the angle with this east-west axis, this angle is 37. It also means that this angle is 53, which is its complement, etc. Okay, and it also means that now L3 is to L2, example, is 5:3 length. So this would be the representation of these vectors. Okay, now so very simple, as you can see. Now one thing I just want to make clear over here is that as geometrical quantities, these arrows are completely movable. So we don't always have to draw the vectors from the same origin. We can, for example, represent F2 like this also. So it's exactly the same vector as that one. So the point of origin of the arrow doesn't matter. What matters is the length and the direction to represent this correctly. So this is the same vector as this one. So these are like movable. So in a sense, if we can just move these around anywhere we like. It does not make any difference at all. It keeps the vector the same. So this is the geometrical representation of vectors. Now, the other way of representing vectors, as you I'm sure are aware of, the second method of representation of vectors is what we call the component notation, or the component representation of vectors. So sometimes we say that say that we are representing a vector in terms of its rectangular components. Okay, so So this is a method of representing vectors that basically makes use of a rectangular Cartesian coordinate system. So this is a method of representation which is reference to a Cartesian rectangular coordinate frame. So as I'm sure all of you are aware, in 2 dimensions we would represent a Cartesian coordinate frame with just a pair of mutually perpendicular axes, which we call the x-axis and y-axis. Okay. So this is in 2 dimensions. Whereas in 3 dimensions, we would represent the coordinate frame with a triplet of axes which are mutually perpendicular. This is where you have to be able to imagine this geometrically, that this is a 3-dimensional diagram, okay, where the plane represented by the xz plane is like the floor of a room you're sitting in. So this is perpendicular to the plane represented by the xy plane, which is like one of the walls. So these are 2 mutually perpendicular planes, and similarly the plane formed by the by the y and z axis is also perpendicular to this. So these are a triplet of planes which are mutually perpendicular, like 2 walls and the floor. So they are perpendicular to each other. Okay. So whenever we represent vectors using this kind of a coordinate frame or a system of axes, this is a 3-dimensional system of axes. First of all, we define the unit vectors. We define what is called these base unit vectors or the standard unit vectors. So they are denoted by I cap, j cap, and k cap. So I cap being the unit vector, that means a vector of magnitude 1 along the positive x-axis. And as you know, the symbol cap stands for the fact that it's a unit vector. So whenever we have a symbol with a cap, it stands for a unit vector. Okay, so that means the magnitude of that vector is unity, whereas this is a vector. So its magnitude could be any value. So this is, you can say, like a general category vector. But when we use the symbol I cap, so it's specific. It is a unit vector along the positive x-axis. Similarly, j cap is a unit vector along the positive y-axis. And k cap is the unit vector along the positive z-axis. So on and so forth. Anyway, right. So when we represent a vector using the component notation, the vector is written rather than drawn, okay, as a sum of 3 mutually perpendicular components. So in 2D, for example, a vector will be represented by an x component into I cap plus a y component into j cap, where ax and ay, these are called the components of vector A. They are basically scalars, okay, which can be negative or positive. So now, how does this look in context of the xy plane or the system of xy axis? Let's understand that next. So if this is our system of axis, then a vector given by this formula over here, which is basically vector A in component notation. Okay, this is vector A in what is called component form in 2 dimensions, of course. Okay, so this would be represented by a corresponding geometrical shape like this. So this is the relationship between the geometrical representation of the vector A and the component notation. So what is the meaning of these two components? As you know, if I drop a perpendicular from this arrowhead onto the x-axis, if I draw a perpendicular onto the y-axis, then we come to our first important set of formulae related to components. This projection or component along the x-axis, this is what we denote as ax, and this projection that we show along the y-axis, this becomes our y component. And coming back to the original vector, if this angle is theta, the x-axis, you can see the relationship between the components and the original vector. The magnitude of the vector is like the hypotenuse of this right angle triangle. So it is square root of ax square plus ay square, and tan theta is equal to ay by ax. Or inversely, we can say that ax is the magnitude of the vector into cos theta, whereas ay is the magnitude of the vector into sine theta, where a is nothing but mod of or magnitude of the vector. So this becomes an important set of formulae for us. The conversion of a vector from geometrical form to component form in 2D or vice versa becomes like this. So this is conversion from geometrical to components. That one is conversion from components to geometrical form. So let's take a quick exercise based on this. So for example, we have a set of vectors given to us. So we want to draw vector arrows and find the magnitude and angle theta with respect to the x-axis for each of these. Okay, so let's say we want to work this out. So we might want to give this a try. Okay, we will discuss. Okay, so let's understand each of these parts. So we have our xy plane. So with respect to that, now we will draw each of these vectors. So the first vector given to us was a, which was 2 I cap plus 2 root 3 j cap. So let's start with that one. So when you analyze this, you can see the x component of a is 2. The y component of a is 2 root 3. So this immediately means that the magnitude of the vector, which is given by this formula, this, if we just substitute these values, you can see that that will become 4. So the magnitude of the vector is 4 units. Okay. And also you can see the angle it makes with the x-axis tan theta is AY by AX. So in this case, that becomes root 3. Okay. So you can see theta is tan inverse of root 3. Okay. And you can see AX and AY are both positive. So it's in quadrant 1, in first quadrant. We can see that theta will become 60 degrees, the first quadrant. So now we know how this vector exactly looks. This vector will be something like this. This is our vector E. Its magnitude is 4 units and its angle with the x-axis is 60 degrees because it is given by this particular formula. Now if we do the same treatment to vector B, which is given to us as minus 4 I cap plus 3 j cap. So let's look at how that looks next. So if you look at vector B, given by minus 4 I cap plus 3 j cap. So this vector, the same thing, you can see it has an x component of minus 4 and a y component of 3. Okay. So you can see that the magnitude of the vector B, when you substitute these here, this will just become 5. Okay. So that's the magnitude now. And now you can see the angle it will make, the axis will be such that tan theta is by bx. So that is minus 3 by 4. So theta is tan inverse of minus 3 by 4. But we have to be careful about quadrants. So you can see that x component is negative, y component is positive. That means it's in second quadrant. So we know that theta here will become 180 degrees minus 37. So it will become 143 degrees. This is the angle it makes with the x-axis. So a vector B, something like this now. Okay, and likewise, when we take the third vector that we were talking about above into account, minus 3 I cap minus 3 j cap. So let's look at this vector. We can see that the x component is negative of 3. The y component is also negative of 3. Space, I'm shifting this down. Yeah. So you can see the magnitude of the vector becomes 3 root 2. And you can also see that tan theta becomes 1. So theta is tan inverse 1. But the important thing is you can see Cx and Cy are both negative. So it's in third quadrant. So this becomes in third quadrant like this. Theta will become 225 degrees. Okay. that is 180 plus 45. So this one will make an angle which is like this now. Okay, so this becomes the vector arrows for each of these three vectors, and this is how we calculate the magnitude of a given vector in component form. Fairly simple. Now, likewise, we can also have a situation where a vector is drawn for us, and we have to convert it to component form. So next, let's look at an example where we want to express the vector shown in component form. So let's say the vector that is given to us is like this. With respect to our xy plane, now we've been given a vector which is like this, let's say. Where this angle is shown to us to be 30 degrees, and the magnitude of this vector is given to us to be 20 units. So when we are converting this to component form, the first thing we have to first figure out is what is the angle that this makes with respect to the x-axis, so that we can find out the x and y components. So we will have to convert the diagram a little bit. Okay. So like I have told you earlier, that remember vectors are completely movable. Okay. So what we have to do is we have to first redraw that vector A or shift that vector A such that it is drawn from the origin. That will just make things easier. That will just make life easier for us to figure out what kind of angle it is making with the x-axis. Just draw the same vector from here now. So it's like this same vector which was drawn here earlier. We just shifted it here. So in that, this angle is 30 degrees. And the magnitude of the vector is 20 units. So now we can see that the angle that this vector makes with the x-axis, that is this angle. So theta is actually equal to 270 plus 30 degrees, that is 300 degrees. Or we can also express theta as minus 60 degrees. Okay. And similarly, now when we draw perpendiculars on the x and y axis, we can understand the components of the vector. So drop a perpendicular onto the x-axis, drop a perpendicular onto the y-axis, and you can see that logically you can understand here that the x component will be positive, whereas the y component will be negative. And straight away make that out. So this is your axi cap and this is your ayj cap. So because of this, you can understand that ax will be a positive quantity, whereas ay will be a negative quantity. So now let's understand them from the formula. So ax is a cos theta. So in this case, this becomes 20 units into cos of minus 60 degrees, which is 20 into half. So it is 10. So as expected, it's a positive quantity. Whereas ay is a sine theta. In this case, it is 20 into sine of minus 60 degrees. So it becomes 20 into minus root 3 by 2. So it becomes minus 10 root 3. So again, as expected, it's a negative quantity. So the vector A now expressed in component form becomes like this. It becomes 10 I cap minus 10 root 3 j cap. So whatever vector we had described by the first diagram over here is now represented by this. This vector is now represented by this component notation. They are one and the same thing. Okay, so this becomes the representation of that vector, which is drawn over here in the component notation. So this is about the component notation in 2 dimensions. Okay. Now let's move on to the next thing, where we look at component notation in 3 dimensions. So this is where we have to really put in some effort to visualize a vector in 3 dimensions. So first of all, when we represent a vector in 3-dimensional component notation, it will have 3 components: an x component, a y component, and a z component. Okay. So here ax, ay, and az are the components of vector E. Now, how do we visualize this, and how do we find the magnitude of this vector? How do we find the angles with the axis, etc.? So that is where, as I told you, we have to visualize this. So let's come back to our earlier diagram of the XYZ axis system. So this is our 3-dimensional coordinate frame. Then in this you can see that the quantity ax I cap, that would be a vector that would be represented as, if I draw it from the origin, it will be a vector along the x-axis. Like this, okay. Ay j cap similarly would be a vector along the y-axis, and az k cap would be a vector along the z-axis, like this. So now if we want to understand what is the vector A over here, what we actually have to do is we have to visualize something like a rectangular or cuboidal box whose 3 consecutive sides are ax, ay, and az. Okay. Now just visualize a rectangular box like this. So in this 3-dimensional rectangular box now, the vector A would be nothing but the body diagonal. It would be the diagonal from the origin, this opposite side. This would be the vector E. Okay. Because as you can see that what we are doing to calculate the vector A is we are summing up the vector Ax I cap with AY j cap with AZ k cap. This is the sum of the three vectors AX, AY, and AZ along the mutually perpendicular axis I cap, j cap, and k cap, which finally gives us. So this vector Ax I cap is summed with this vector Ay j cap, is summed with this vector Az k cap. So geometrically, you're displacing yourself from the origin along the x-axis by Ax, then perpendicular to it along the y-axis by Ay, then perpendicular to it along the z-axis by Az to get to this point. So your net displacement is from the origin to this opposite corner. So you can see that the interpretation of this is like the vector A is represented by the so-called body diagonal of a cuboid with sides Ax, Ay, and Az. So this is the relationship between the geometrical interpretation and the component notation in case of 3 dimensions. So once you know that, it's very easy to understand that the magnitude of such a vector will be equal to square root of Ax square plus Ay square plus Az square. So this becomes our formula for the magnitude of such a vector. And about the directions we will discuss in a moment. So for a 3-dimensional vector, expressed in component notation, we also define something called direction cosines. They are respectively called cos alpha, cos beta, and cos gamma, where alpha is the angle of the vector A with respect to the positive x-axis. Beta is the angle with respect to the positive y-axis. Like this, gamma is the angle with respect to the positive z-axis. Now we're going to look at the formula for the direction cosines, which we will justify at a later stage when we discuss about dot products. The direction cosines, if you're already aware of this, you will know, are given by these formulae respectively. And they have an important identity between them, that cos square alpha plus cos square beta plus cos square gamma is equal to unity on this. So this is also an important identity to understand. And this is pretty easy to justify or understand because you can just substitute the values of cos alpha, beta, and gamma, and you know that magnitude of the vector A we have just seen is given by that formula. So that in itself gives you a justification of this. Okay, so this is an important aspect. All right, so let's look at a quick example or two of this. Find the direction cosines and the angles with respect to x, y, and z axis for so we have this and we want to find the angles with respect to the xyz axis. So we'll first of all make use of direction cosines. So the way to solve this problem will be very simple, that we can see that Ax is root 2, Ay is minus of square root 2, whereas the z component is 2. So from this we can also see the magnitude of the vector A. So that will become square root of 8 or 2 root 2. So we can see that the direction cosines we can directly express from the formula. Cos alpha is Ax by A. So that will become, as you can see, root 2 divided by 2 root 2. So that will become 1 by 2. Cos beta will become Ay by A. So this is minus root 2 divided by 2 root 2. So that will become minus half. And cos gamma will become Az upon A. Nothing but 2 divided by 2 root 2. So that is 1 by root 2. So once you have figured this out, now next thing you can see very easily from this, the angle alpha with respect to the x-axis is cos inverse half. So alpha will become 60 degrees. Beta, the angle with the y-axis, the cos inverse of minus half. So that in this case will become 120 degrees because it will have to be an obtuse angle. Its cosine is negative. And gamma, the cos inverse of 1 by root 2. So gamma will be 45 degrees. So these are the angles with respect to the x, y, and z axis respectively. So that is how we make use of the formula of direction cosines solving this type of a question, right? So this is the basic part about representation of vectors. Okay, so once we are clear about this thing, representation of vectors, we can next move on to algebraic operations involving vectors. Before we move on to algebraic operations involving vectors, we should just keep mindful of a couple of important facts. First is something called a null vector, which we can denote with a symbol like this. So a null vector is it's a vector of magnitude 0. Something we should know about. Okay. Unit vector we've already talked about. A unit vector is represented by a symbol like this. It is a vector of magnitude unity. Or 1. Now we should also understand that as far as vectors represent physical quantities, as far as we're talking about vectors representing actual physical quantities, further we divide vectors into two categories. What is called polar vectors and what is called axial vectors. So polar vectors are vectors to represent physical quantities that act along a line of action. So the direction of that vector is the line of action. For example, force. So force acts along a line of action and that becomes the direction of the vector. Velocity. Velocity acts along a line of action. So that is the direction of the vector. Whereas axial vectors, they represent physical quantities which involve rotation about an axis, and the direction of the vector, the direction of an axial vector, is nothing but the axis of rotation. Is the line of the axis of rotation. So examples of these are all angular quantities like torque, okay, angular velocity, angular momentum, and things like this. So in the case of axial vectors, the direction of the vector represents the axis about which the rotation is happening for that particular physical quantity. Whereas in the case of polar vectors, the direction of the vector represents the line of action along which the vector is acting. So this is also something that we should be mindful of. So having understood all this about vectors and their representation and their types, etc. Now let us come to the next aspect of vectors, which is basically vector algebra or vector operations. Okay. So mathematical operations of vectors, or what we call vector algebra. Okay, so the first and simplest type of operation is the multiplication of a vector by a scalar. So there is nothing much here. For example, a very well-known equation like F is equal to ma. Here on the right hand side, this is mass multiplied with acceleration. So acceleration is a vector, mass is a scalar. So for example, if I say that the vector B is 10 times the vector A, that means the magnitude of vector B will be 10 times the magnitude of vector A, and direction of B will be along A. So for example, here, if the vector A is like this in this direction, then the vector B will be parallel to it in the same direction but 10 times in size. So this is the vector A. It has a magnitude A. The vector B will have a magnitude of 10A, but it will be at same direction. So this angle will be the same as this because they are parallel. So that is the meaning of multiplying the vector with a positive quantity. Okay. Now, of course, you always have the idea that you can also multiply a vector with a negative quantity. So suppose we have C is equal to minus 2E. So the negative sign here means that the direction becomes opposite. So the magnitude of the vector C remains 2 times magnitude of the vector A, but direction of vector C is opposite to vector A. So in this case, we also say that A and B are parallel vectors. And in this case, we will say that A and C are what is called anti-parallel vectors. So once again, if this is my vector A, then my vector C will look something like this. It will be opposite in direction, but double in length. And of course, we have the exceptional case of multiplying a vector with 0. So that becomes a null vector. This is a trivial case, nothing exceptional over here. So that's one of the ways in which we can come up with the null vector, okay, or one of the significances of the null vector, that if you multiply any vector with 0, with the scalar 0, you get the null vector. Now let's move on to our next vector operation, which is addition of vectors. As you know, has a lot of wide applications in physics, and we'll spend quite some time on addition and subtraction of vectors. So the first thing we'll look at in addition of vectors is vector addition by triangle law or parallelogram law. Or the addition of two vectors. So of course you need to understand one thing, that keep in mind one thing, that two vectors can only be added when they are of the same physical quantity and they are represented in the same unit. So we can only add a displacement with a displacement which is in the same unit. So if one vector is a displacement in meters and we want to add a second vector, it has to be a displacement. We cannot add displacement with force or displacement with velocity, and it has to be expressed in the same unit of meters. Okay, so that goes without saying. Having said that, if we have two vectors which are, so triangle law, as you know, is a geometrical method of adding two vectors. So if we have two vectors given to us by their vector arrows, so this represents vector A, and suppose this represents vector B, such that we know the magnitude of vector A, the magnitude of vector B, and the angle between A and B, angle of vector B with respect to vector A. This is known. Okay. These quantities are known. Then we can find out A plus B. Okay. This is called the resultant sum of vector A and B. So this we can find out by using the triangle law. So let us look at how this exactly works. Okay, so the process of addition of the vectors, like geometrically what we'll have to do here, as you know, to add these two vectors, is we will have to redraw the vectors in a diagram in a method which is called head to tail. That is, just imagine that we are talking about two displacements A and B, for example. So if we are making the resultant displacement of A plus B, that means from some starting point, we first make the displacement A like this. Okay. And once we have completed this displacement A, next we make the displacement of B. So we have to pick up the B vector arrow, or imagining that it's a displacement arrow, and we have to make that second displacement of B immediately after completing the displacement of A. So from our starting point, we made the displacement of A, and then immediately after A, we made the displacement of B. So if we place the vector arrow of B over here, this is the same arrow as this one. We end up at this point. So this becomes our final point, whereas the origin of A, or the starting point of A, was our starting point. So our net displacement, which is basically the resultant of A and B over here, that you can see becomes this one. So that is why it is called the triangle law, because the resultant is expressed as the third side of a triangle formed by A and B as two consecutive sides. So that is why this is called the resultant. The resultant of A and B, we can represent by the symbol R. Now in this diagram, the angle between the vectors A and B is nothing but this angle. It is the exterior angle of this triangle. Now, as I said, I will not be getting into the derivations in this session because it's a revision session. So you can look it up from a reference book, but it's very easy to trigonometrically derive this using a right angle triangle like this, that the formula that we ultimately get by solving this triangle is that the magnitude of A plus B is given by square root of A square plus B square plus 2ab cos theta, and the angle that the resultant makes with respect to the vector E, say this angle is alpha. So this is given by the formula tan inverse of b sine theta upon a plus b cos theta. So this is one of the most important aspects and most important applications of vector algebra that is used throughout in physics in various chapters. That is addition of vectors, and if we are adding two vectors geometrically, we make use of the triangle law. So the statement of the triangle law shows us that if we are adding two vectors, we should draw them consecutively, one after the other, that is head to tail, and as two sides of a triangle. And the third side of the triangle becomes the resultant, and the magnitude and the direction of the resultant is then given by these two formulae. So that's your triangle law for application. So let's look at some quick examples of the application of this. So we can start with something quite straightforward. Suppose the magnitude of one vector is, let us say, 20 units. The magnitude of another vector is, let us say, 15 units. And the angle between them, that is, so you want to find the magnitude of a plus b and the angle of the resultant of a plus b with respect to the vector E. So in this type of a question, we can directly make use of the statement of triangle law and the formula of triangle law and work this out. Okay, so let's just quickly look at the application of the formula. So here, mod of a plus b, we'll just substitute this. So here E we will substitute as 20, B as 15, but theta is 90 degrees. So we can see that cos theta becomes 0. So this on substitution, it just becomes this much, which is 25. So there we are. That's directly our magnitude of a plus b. And as far as the angle is concerned, we have alpha is tan inverse of b sine theta upon a plus b cos theta. So sine theta becomes, because theta is 90. So this just becomes tan inverse of 15 by 20, which is basically tan inverse 0.75. So that is nothing but again 37 degrees. So now you can support this result with a very simple geometrical interpretation also, that if you look at this information given to us about A and B, it will correspond to a vector triangle like this, that the vector A is 20 in length, the vector B is perpendicular to it, and it is 15 in length. Angle is 90. So naturally, the resultant of A plus B will become the hypotenuse of this right angle triangle. So that will become 25. And this angle alpha will become, as you can see, this is a 3, 4, 5 triangle. So it will become 37 degrees. So this geometry nicely agrees with the formula based calculation that we have done. So that is about the addition of two vectors by triangle law. Let's look at another example. Now we have this situation given to us that magnitude of the vector E is 10 units. Magnitude of the vector B is 20 units. Okay. And given that A plus B is perpendicular to the vector A. So we have to find, first of all, theta, the angle between A and B. And we have to find the magnitude of A plus B. And we have to find the angle. Oh, sorry. We just have to find this much. So let us look at this question next. So you might want to try this out yourself first. Okay. So I'm putting up the solution next. Okay. So here we will start with this thing, that this is perpendicular to A. So if we go with the formula based solution, we know that alpha, which is tan inverse B sine theta upon A plus B cos theta, should be 90 degrees. So that means B sine theta upon A plus B cos theta should be tan 90, which is an undefined quantity. So the denominator should be 0, because this whole fraction is undefined. So A plus B cos theta should be 0. So this tells us that cos theta should be equal to minus A by B. Now we substitute the value. So it should be minus half. So that tells us immediately that theta is cos inverse of minus half, which means that theta is 120 degrees. Because we know that cos 60 degrees is half, therefore cos 120 degrees is minus half. So we make use of that. Okay. And once we know theta is 120 degrees, therefore we also know that the magnitude of A plus B by the formula method will become, so here we'll substitute A as 10, B as 20, and theta as 120 degrees, or cos theta as minus half. So when we do that substitution next, you can see we will get okay. So if we take 10 common, ten root 3. So magnitude of A plus B becomes 10 root 3 units, and theta is 120. So these are the two answers. So just take a look at the full solution once quickly. Then we'll also look at the the geometrical interpretation of this. All right. So now if we want to geometrically understand what's happening here, we are obviously dealing with a situation where A and B have to be such that their lengths are in the ratio 1:2, but they are like this because the resultant is perpendicular. So it has to be an obtuse angle. So this is of length 20. This is of length 10. So this is the angle theta between them. So we can see it has to be obtuse. because it is given to us in the question that the resultant of A and B is perpendicular to A. So again, we are dealing with a right angle triangle, but this time this angle is 90. The angle between the resultant sum of A and B, and this angle is 90. So you can see this information here will correspond to this. So we can also solve this as a triangle. So we can see that mod of A plus B is just that side. So it is 10 root 3. Okay. And we can see that this angle, suppose we denote this as beta, we can see that beta is tan inverse of root 3 or 60 degrees. So therefore naturally theta is 120 degrees. So both the results are justified by the geometrical. Okay. So this is about the addition of two vectors by the triangle law. Now, next thing similarly we move on to is like a second part of triangle law for the subtraction of two vectors. Okay. So the difference of two vectors or the subtraction of two vectors by triangle law. So once again, if we have, let's say, a given vector A and another given vector B, such that we know the magnitudes of the two vectors and we know the angle between them. So these are known quantities. And we want to find out the vector difference. This, okay. So first of all, we interpret this vector difference as the sum of the vector A with the vector minus of B, okay, where minus of B is a vector opposite to B but of same magnitude. So what we have to now do is we have to construct a triangle where we are adding the vector A with the vector minus B. So that vector triangle will now look like this. First start by drawing the vector A. And then instead of the vector B, we construct from it the vector minus B. That is equal and opposite. So minus B will also have the same magnitude as B, but it will have the opposite direction. So we pick up that vector minus B and we place that vector on the head of A. So this is the vector minus B now. Now also notice that if we had placed the vector A and B together, okay, then the angle made by A with respect to B, that was theta. So for the vector A placed with the vector B like this, this angle here was theta. So now the vector minus B is along the same line. So this angle here becomes theta, or the angle between the vector A and minus B actually becomes 180 degrees minus theta. So that is why now when we calculate the difference of the two vectors, which is this side of this triangle, This is A plus of minus B. So in other words, this is A minus B. And let's say this angle is beta. We can make use of our formula of the triangle law from earlier. We can see that because we are doing this operation, what we'll end up with as a formula is that magnitude of A minus B will become root of A square plus B square plus 2ab cos of 180 minus theta. So cos of 180 minus theta is minus cos theta. So this becomes minus 2ab cos theta. Okay. And likewise, that angle beta becomes tan inverse of b sine 180 minus theta, which is the same thing as sine theta, upon a plus b cos 180 minus theta. So that again becomes minus b cos theta. Okay, so these formulae, they get modified like this because cos of 180 minus theta is the same thing as minus cos theta, whereas the sine of 180 minus theta the same thing as sine theta. Okay. So that is how these formulae for the application of triangle law for difference of two vectors come about. Okay. So let's look at a quick example. So now given to us, suppose that magnitude of vector A is equal to magnitude of vector B is equal to 50 units, and theta is equal to 120 degrees. That is the angle between A and B. So find magnitude of A minus B and the angle of the vector A minus B with respect to the vector E. Okay, so let us look at the application of this question with the triangle law formula that we've just discussed, but the second triangle law formula, the one for the difference of two vectors. Okay, so let us quickly look at the application of this. So if we go with the formula based method, then we can just substitute over here. Okay. So we will substitute A and B as 50 each. We will substitute cos theta as cos 120, which will become minus half. Okay. So actually this will now become into minus half. So it will become 50 root 3. So that's our magnitude of A minus B. You can, for example, also understand this from a vector diagram. So if this is our vector A and this is our vector B, which is at 120 degrees to it. They're both of 50 units each. And this angle theta is 120 degrees. Now remember, when we are doing the vector subtraction, we have to construct the vector minus B from the vector B. We're not adding A with B, we are actually subtracting. So we'll have to draw the vector minus B here. So that will be a vector of same magnitude, 50 units, but the direction being opposite. So now this angle is 120 degrees. Okay. And finally, our vector difference is going to be this one. This will be our vector A minus B. So you can quite easily use the property of, um, isosceles triangle. Since this side is equal to this side, so this angle will be equal to this angle. So this will be 30 degrees. If you drop a perpendicular here, it will bisect this side. So for this right angle triangle, you can see that x will be 50 cos 30. So that will be 25 root 3. So obviously you can see that the whole side a minus b is 2x. So that becomes 50 root 3. So that justifies this, that this side should be 50 root 3. And this is also showing us that angle beta is 30 degrees. So let's get that by formula also. So beta is tan inverse of b sine theta upon a minus b cos theta. So sine 120 root 3 by 2. So when you substitute this, this will become tan inverse root 3 by 2 upon 1 plus half. 50 will cancel out, so you will get tan inverse 1 by root 3, 30 degrees. So again, this checks out with the geometrical method. So this is a quick example of the application of triangle of a subtraction of two vectors. Okay. So this brings us almost to a close of today's session, but we will take a quick look ahead of what we're going to do in the next session. So we are going to start up our next session with parallelogram law as a sort of combination of triangle laws for addition and subtraction. So we'll see how to construct a vector parallelogram and within that parallelogram we'll see how to the addition and subtraction of two vectors within the same geometrical shape instead of drawing two triangles separately. So how we'll understand the parallelogram law is like this, that suppose this is a vector A and this is a vector B. And this angle between them is theta. And magnitudes are as usual like this, and theta is known. So when we look at individually the two triangle laws for sum and difference, we can see that construction of the triangle for the sum is like this. So the third side of this triangle gives us the sum of A and B. This angle is alpha. We already know the formula for the magnitude and the angle alpha. But similarly, if we are calculating the difference of these two vectors, we have to construct it this way. We first draw the vector A, and then to that we will construct the vector minus B. So if this was the vector B, then the vector minus B will be like this. So here, if this angle was theta, here this angle will become theta. So the difference of the two vectors becomes this one. And this angle we denote with beta. And we've already seen the formula for mod A minus B and the angle beta. Now, the important thing here for parallelogram law is that we will combine these two into one shape. Okay, so what we can next do is we can construct a new figure where we draw both A and B from a common origin. Instead of drawing them head to tail, we draw both these vectors A and B from a common origin. This is a vector A and this is a vector B. Okay, then we complete the shape of the parallelogram formed by these two by drawing two other parallel lines. So this is the vector parallelogram formed by A and B. This is the parallelogram with A and B as adjacent sides. Now, if you look closely in this parallelogram, we have both the sum and difference. If you look very carefully, if I draw this diagonal from the common origin to the opposite side, is the same construction as the first triangle. So this diagonal becomes nothing but the resultant sum of A and B, and this angle becomes that beta, because see, this angle is theta, same as this angle theta. So this triangle here is basically present over here. This triangle is the same one. And likewise, if you look at the secondary diagonal, the diagonal that you get by joining the head of B with the head of A, this one. Now you can see that that is nothing but this same construction as this. So this is now my A minus B. So you can see that in the same geometrical diagram, I've got both the physical quantities A plus B and A minus B. So you can see that this particular triangle that we had here, this triangle is this one. This triangle. So the parallelogram law, it combines the vector triangles that represent A plus B and A minus B. So we'll take a closer look at this in the next edition of this series, and we'll see how using some of the properties of the parallelogram, the geometrical properties and special cases, etc., will help us develop some methods for dealing with sum and difference of vectors. Okay. So hope you have enjoyed today's session and managed to revise the basics of vectors carefully. So just to go through it again, we started with the understanding of the representation of vectors, the two methods of vector representation, the geometrical method and the component method of representation. And from there on, we next looked at the vector operations, starting with the multiplication of a vector by a scalar, and then moving on to sum and difference of two vectors using triangle law, and how the two triangle laws can be combined into the parallelogram law, and how their formula are developed. So that's it for today, people. Wishing you all the very best.